So welcome to the last part of lecture 32. In this part, what we want to do is we want to finish up this the proof of this theorem, which is that when you have a normal operator and if you know the eigenvalue, you actually automatically know an eigenvalue of the adjoint, which is its complex conjugate. So in the last part, we proved this claim that if t is a normal operator, then we can construct another normal operator from it. And so let's finish the proof. Okay, let's say that V is the eigenvector of lambda for t. And then, since V is an eigenvector, right, when we plug V into the operator, this operator, we get 0. Okay, that's simply because TV is equal to lambda IV. That's another way of saying that V is the eigenvector of lambda. So that means that the norm of this vector is 0, right? And this, by definition, is the inner product of t minus lambda IV. Here, I'll put it all in, clean that up. It's a little messy. Try that one more time. This is the same as t minus lambda IV, the inner product with itself. Okay, so there we go. And now, oh, actually, I don't even have to go. I'm making this more complicated than I need to. The point is that this is equal to the norm of this guy. And why is that? This is the last result since t minus lambda I is normal. So let me just show you why, the pieces. So the last result showed that this operator is normal, and so that was kind of the claim. And now we go back to the first result, which says, well, when you have a normal operator, the t and its adjoint preserve the norm. Right? So that's exactly what we have here. This is our operator, it's normal, so these guys preserve the norm. And now the point here is that you can expand this out, right? So this is t star, or the adjoint of t, times the conjugate of lambda I, v, right? So this is the same thing. I'm just kind of bring the adjoint inside. So we get that the conjugate of lambda is an eigenvalue of t star. Okay. So you may have actually seen some special case of this if you took Math 2LA3. If you didn't, that's okay. And we may have actually even mentioned it in Math 1B03. And from a matrix point of view, what it's saying is that if lambda is an eigenvalue of a symmetric matrix over A, then the conjugate of lambda, which is just itself, is an eigenvalue of A transpose. So actually, when you have a symmetric matrix over the real numbers, all the eigenvalues are the same of the two matrices. Okay. So I know there's kind of a lecture, there's a lot of kind of deep stuff going on. Here's kind of the last thing that's kind of useful to know is that when you have a normal operator, the eigenvalues corresponding to distinct eigenvalues are orthogonal. Okay, so that's what we want to prove. So let's say that we have distinct eigenvalues, lambda 1 and lambda 2, and we have v1 and v2 are the corresponding eigenvalues. Okay, well, since t is normal, what we know is that, and this is just by what we proved above, that when you now plug v1 into the adjoint, you get the conjugate of lambda 1 times v1, and you get that the conjugate of v2 is equal to the adjoint of v2 plugged into the adjoint of t will give you the conjugate of lambda times vt, and that should be a 2. Okay, so that's coming from the previous result, and now what we're doing is we're looking at what happens when we take v1 and v2, the inner product of them, scale it by this constant, lambda 1 minus lambda 2. And the thing to pay attention to is that this number here is not 0. Okay, so we just follow our nose. We start using all the properties of inner products. We bring the constant in to the first slot. Then we expand out this in the first slot. So we get lambda 1 minus v1, lambda 2 times v1, v2. And we can break this inner product up as lambda 1 v1 comma v2. And over here we get lambda 2 v1 comma v2. Oh, sorry. Yep, that's right. Okay, and now this guy right here is t evaluated at v1, v2, and this guy here is t evaluated at, oh, let me change this around. Here I'm going to push the lambda to the other side, so I have v1 conjugate of lambda 2, v2. And then I notice that, oh, this is tv1 comma v2, the inner product of that. This is v1, and this is t star vt, right? So I'm using this fact right up here. And now I'm using, you apply the adjoint, right? I can push this t to the other side. So this is v1 t star vt, and then I have v1 t star vt, but these guys are the same thing. So this is 0. Right? So what we have is this constant times this inner product gives me 0. This number doesn't equal 0, so this forces the inner product of v1 and v2 to be 0. Okay? And remember what that means is that, i.e., they're orthogonal, which is what we wanted to prove. Okay, so there was a lot of kind of deep results in today's lectures. We learned about the big things that we learned about are self-adjoint operators and normal operators. And if you're getting confused about those, just kind of remember that the self-adjoint operators kind of correspond to symmetric matrices over the real numbers, or those matrices who equal its conjugate transpose. And normal operators are those operators where the matrix A and its transpose commute, or the matrix A and its complex conjugate, or the conjugate transpose also commute. Okay, so that's kind of what we've been looking at and some of their properties for today. Okay, so hopefully I didn't lose too many people in today's lecture. Take a look at the book, reread it, and we'll kind of look at section 7b starting in the next lecture. Okay, have a great day.